All right. Today I will be doing a few examples on separable differential equations. So I'm going to do a quick intro on differential equations. A differential equation is an equation that has a differential equation is an equation that involves a function and a known function. The derivative of the function, maybe derivatives because then we have second and third order derivatives of the function of an unknown function, okay? Some examples that I gave in class look like, say you want to find a function whose derivative equals itself. That's just a differential equation. A second example I gave in class was the gravity acceleration is 32 feet per second squared. That's the second derivative of a position function. I can create just a random one, say y prime equals x squared times y. That's a differential equation. We don't know the function, but we're trying to find a function whose derivative equals the function multiplied by x squared. Okay, I can have another one that looks like this: y double prime plus 2y prime plus y equals 0. This is another differential equation, and this is what we call a second order differential equation. These two are second order differential equations. Because the equation now involves the second derivative of the function. Okay, these two are first order differential equations. These two are first order differential equations. This is the first order. This is the first order. Okay, where do these things come from is one of the things that, okay, let me first mention the solution to some of these. Okay, so y prime equals y, we discussed this in class. To find a function whose derivative equals itself, the easy solution, the easy answer is y equals e to the power of x. But y equals any constant multiple of e to the power of x is a solution. This is called the general solution. To the differential equation, to this differential equation. That's the general solution. A specific solution would be y equals 5 times e to the power of x. So the difference here is this one is a class of functions. Let me explain this. So if this is your y-axis, let me put some x and y-axis here. This is your y-axis. And this is your x-axis. Here's your x-axis. Here's your y-axis. Y equals c e to the power of x is a function that passes through the point c when x is 0. That c could be here. That would make it an exponential function that goes like so. Or it could be here, an exponential function that goes like so. Or a slow one like this. Or c could be a negative one, which means it's the exponential function that... So any of these curves is a solution. So that c can change. Now, looking at that one, that's the one that goes through the point 5. So that's a particular solution. So if you wish to pick the one that has y prime equals y and y at 0 equals 5, this has a particular solution. Okay, that's the solution to this differential equation. This one is called an initial value problem. We don't usually call it a differential equation problem. We call it an initial value problem, which means it's a differential equation with some initial value given. Okay, so that nails down that particular solution that solves this differential equation with this condition here. Okay, so that's what an initial value problem, or an IVP, is. So back to these examples. If I know the initial position and I know the initial velocity, I can write an initial value problem with this gravity differential equation. All right. Where do these things come from is one of the motivations. Let me just say a couple of reasons where we get a differential equation. So population is one of them. The rate of change of the population, meaning the derivative of the population, is always, or in many instances, is proportional to the existing population. The existing population meaning P of t. In other words, P prime of t is some constant multiple of P of t, where this constant depends on what kind of population we're looking for. For example, if you're looking for a rabbit's population versus elephant's population, the proportionality constant is different. Or bacteria, or the temperature, many things, but that's a constant, k, the proportionality constant. This is the differential equation y prime equals k times y, much like the one we had with y prime equals 1 times y. Okay, another one is coffee. So if T of t is the temperature of your coffee, then the rate of change of the temperature is proportional to the difference between the ambient temperature and the current temperature of the coffee. This is the current temperature of the coffee. This is the ambient temperature, the room temperature, or if you put it in the fridge temperature. Okay? So it's proportional to the difference. So T prime of t is some constant times T0 minus T of t. This constant depends on many things, but it's a constant for a particular situation. So this is like y prime equals a constant times the ambient temperature minus y. That's a differential equation. These are constants. Okay, I could say this may be 72 degrees for a room temperature. So that is what that differential equation looks like. Now let's go to a separable differential equation. What's a separable differential equation? A separable differential equation is always a first order differential equation. We don't do too much. We don't do second order, third order differential equation. A separable differential equation is something that looks like the derivative of a function equals a function of x multiplied by a function of y. So if the derivative is given as the product of two functions, one is a function of x, one is a function of y, we call it a separable differential equation. And this has a very nice technique of solving this differential equation. Let me give you examples here. I have y prime equals y. In this case, f of x is just a function 1, and h of y is the function y. It's a product of two functions. One is a function of x, one is a function of y. Okay, y prime equals sine of x multiplied by y squared. That's just a separable differential equation. Okay, y prime equals x plus 2y is not separable. This is not a separable differential equation. So the technique that we do for separable differential equations would not help solving this differential equation. This seems easier than that, but when you see it, but in actuality, they're not. It's not that easy. I mean, it's not difficult, but it's not a separable differential equation. So separable differential equations look like this. How do we solve them? Let me just show you one example first. Okay, let me put this one. Y prime equals x squared times y is a separable differential equation. So how do we solve these separable differential equations? I'm just going to start with this to explain how we solve and why we call it separable. Okay, so dy by dx, this differential equation, dy by dx is x squared times y. This is the same thing as 1 over y times dy equals x squared dx. That's what it means. I just brought the y over to the side. So 1 over y dy is x squared dx. So if we integrate the left side, it's only a function of y, we can integrate that. And the right side, it's only a function of x, we can integrate this. So the integral of 1 over y dy is natural log of y plus c. I'll call it c1. And the integral of x squared is x cubed over 3 plus c. So we have essentially solved the differential equation. These two are just arbitrary constants. So we're going to move this and add it to that one. So natural log of y is x cubed over 3 times plus c. Then we can rewrite y. We'll do that in the next examples. We can solve for y. Maybe here. We can do that in the next examples. So basically, a separable differential equation looks like a differential equation in a form of y prime equals f of x times a function of y, h of y. So I will come back to that. So y prime is f of x times h of y, which means that dy over dx is f of x times h of y, which means that dy over h of y equals f of x times dx. In other words, 1 over h of y dy is f of x dx. If I call this guy 1 over h of y, if I call this guy g of y, then this differential equation looks like g of y dy equals f of x dx. So that's what a separable differential equation looks like. Neatly separate the functions of y on one side dy and the function of x on the other side dx. Now to solve, integrate. After we integrate, then we usually solve for y. Okay, most of the time it's solvable. Occasionally it's not. So we solve for y and write it as y equals some expression of x. Okay, so let me do a couple of examples. So basically we have separable differential equation. We write it as that. We write it as that first. That's first step. Then integrate both sides. That's what separable differential equation is. So let me do an example here. The first example is the good old y prime equals y equation. This is separable. This says dy by dx equals y. It says that dy over y equals 1 times dx. Integrate 1 over y dy and integrate 1 dx. Will give you natural log of y plus a constant equals x plus a constant. Because c is just an arbitrary constant, you can combine them and write it as just one constant. Okay? Now trying to solve for y, changing this log expression to exponential expression will give me e to the power of x plus c, or absolute value of y is e to the c times e to the power of x. But that's also, let's call this c1. That's also another arbitrary constant, e to the power of a constant. It happens to be a positive constant, but I'll call it c2. Well, the absolute value of y is c2 times e to the power of x, where c2 is a constant, a positive constant. But I can rewrite this as y equals plus or minus c2 e to the power of x. And notice this is also another arbitrary constant. Okay, but this can be positive or negative. So I'm going to just write it as c e to the power of x. And that's my general solution. And if you remember, in class we looked at that one and we said that the solution to this is y equals c e to the power of x, just simply exploring possible answers. Okay, and this is just the right way of solving this differential equation. And this is a separable differential equation. All right, let's do some more. Okay, the second example is y prime equals x squared over y squared. This is a nice separable differential equation. You can see that if you write it as dy by dx equals x squared over y squared, or y squared dy equals x squared dx, integrate and integrate. This gives you y cubed over 3 plus some constant, and this gives you x cubed over 3 plus some other constant. Multiply everything by 3, so get y cubed equals x cubed plus 3c. This is just another arbitrary constant, so let's call this c1 and let's call it c. Okay, so we're going to write it as y cubed equals x cubed plus c. There's just no reason to multiply by c by 3. Now take the cube root. The cube root of x cubed plus c is your final answer. Okay, I just want to say that this is not the same thing as cube root of x cubed plus c. These two are different things. These are different equations for different solutions, for different differential equations. So it's not the same as that one. So let me just box this. And that's the solution to this differential equation. All right. Okay. Let me give you a quick quiz and end this lesson. I'll come back to some more examples when we start after the break, okay? The quiz is solve this differential equation, y prime equals x over y. You just follow this pattern and solve for y prime equals x over y. All right, and have a nice break. I will see you when we come back from the break.